Consider a circle of radius 1 centered at the origin. Here, we've seen this a million times. I'm going to think about starting at the origin, and I'm going to draw a straight line until I strike the circle at a certain space, and I'm going to keep track of the angle I use with the letter T. Right here, we get a point x comma y at that position. Now this is a circle of radius 1, so it goes by x squared plus y squared equals 1. And we know a little bit more than this. If I were to drop a line down like so, and look at this triangle that I formed, it goes something like this. I'll draw it again over here, because I want you to see. Notice the height of the triangle, since I'm in the first quadrant, the height of the triangle is y, and the base of the triangle is x. So we know that cosine of t, that equals adjacent over hypotenuse. And this, I should mention, the radius is 1, because the circle has radius 1. So cosine of t equals adjacent over hypotenuse, and so we just get x equals cosine of t. Similarly, do the same thing for y, and we get y equals sine of t. So these right here are referred to as parametric equations. The reason why is because I've introduced a letter t called a parameter. This one letter t can control both x and y. It's very useful in a lot of context, and we're going to take a look at it right now. First and foremost, let's get the calculator to graph this to show you that your calculator is capable of doing this stuff. So we're going to try to graph this circle with this equation, but I'm not going to put this equation in here. I'm going to put these equations into the calculator. Here's how you do it. Bring up your TI, or whatever it is you're using. You can make the adjustment as needed. Turn it on, and the first thing you're going to need to do is change the mode. By the way, you should have been in radian all this time. If not, it's probably cost you some points. And I'm going to go down to the fourth line where it says func par pol sequence, and I'm going to go over to par. That stands for parametric. Hit enter, and then let's go ahead and put in our equation for a circle. Let me clear this and clear this. For x1, we had cosine of t, so I'll write in cosine. And when you change to parametric mode, when you hit X, this button that usually gives you an x, it'll now give you a t. Hit enter. And for y1t, put in sine of t. And this is what we're going to graph. Now, probably take a look at, let's take a look at the window. And let me come back to this for a second. Everybody know that in radian mode, the angles that we usually start with start at t equals 0 radians. But as you go around, like you get up to here, this is t equals pi over 2. As you keep going counterclockwise, you get t equals pi, t equals 3 pi over 2, and then when you get back it's 2 pi or back to 0 again. You got all the angles in between, pi over 4, pi over 3, whatever, they're all in here included in that. So in order to get a complete graph, I only need to let my t go from 0 to 2 pi. So that's what I'm going to do. I'm going to start my t minimum at 0, and I'm going to put my t maximum at 2 pi. And you don't have to memorize digits of pi for this. It'll actually let you put it in like this, 2 pi. Hit enter. Notice it changes to a decimal on you. change the t step, by the way, yours probably says something closer to 0.13 and a bunch of other decimals. X min and max, I know yours have got to be different from mine, but since this stretches from -1 to 1 in all directions, I'm just going to let my x min be -1, my x max be 1. So after you've made these changes, you don't have to change anything else. Click Graph. And you'll see what appears on the screen looks like an oval. The reason why is because your screen is wider than it is tall. If you want it to look more circular, click Zoom and then hit number 5 for Z square. And now adjust the dimensions so that the circle looks like a circle. But what I wanted you to notice, go back to the window for a second. What I wanted you to notice that if you draw it a little bit slower, I want you to notice how it is actually drawn, in what manner it is actually drawn out. So if by putting t-step 0.01, it's going to take values at every point 0.01. So it'll go 0, 0.01, 0.02. Before it would take it in larger chunks. Now when you graph, it'll be a lot slower. But look how it's drawing. It's starting at 0. Here it goes. There it gets to pi over 2. Keep going. Here it comes down to pi. Now it's coming down. 5 pi over 4. 3 pi over 2. Coming back up to 2 pi. And it stops there because that's where I told it to stop. And you can even do a trace here. If you click trace, it'll start you at t equals 0, and it tells you the x and the y values. If you click to the right, which means to increase t values, you can see it make its way around the circle and it gives you the x and y values. So I think pi over 4 is somewhere around 0.785, so let me get around that. And you can see the x and the y values are getting close to being the same. I think it just jumped over it there. So right around there is about pi over 4. They're pretty close to being the same. And you can adjust these and all those things that you need. But remember this setup. Drawing a circle here is simpler, I think, than doing it as a regular functions, because for this particular equation, when you solve for y, you have to do a plus and a minus in order to get the top and bottom of the circle. This doesn't require you to do that. When you look at the graph, you might not even say that's a function. It is a function. Here, x and y are dependent variables, and t is the independent variable. Whatever t does, it affects x and y. Now, going back to the way the graph was drawn, we can draw arrows to indicate that the graph is traced out. Try to make my arrows thick, in a counterclockwise direction. That's what these arrows tell me. This is going to be very important, especially in Calculus 3. Where you're going from where you're at is important. So if we start at 0, the arrow tells me to proceed in this fashion, counterclockwise. You'll need to keep track of how things are drawn and whether they go left, right, up, down, or whatever, depending on what t does. I'm going to call that first thing I did example 1. And for the next one, I want to graph x equals 2 cosine cubed of t, y equals 2 sine cubed of t, and I'll let t go from 0 to 2 pi. I don't need to do more than 2 pi for this particular thing because both sine and cosine have a period that's 2 pi. So whatever they're going to do, they've completely done in this one length of 0 to 2 pi. So let's get it into the calculator. It's going to look like this. x1t is going to look like 2, and you probably will need to do this. Cosine of t to the third. I think you can raise it up like that. And then your y1t will equal 2 sine of t to the third. Let's go ahead and graph those and see what happens. And we'll adjust the window as needed. So I have 2, and I'll put cosine of t in parentheses. And raise that to the third power. And then come down. For y1t, I'm going to put 2 I forgot my parentheses around sine. And my window, I think, still had 0 to 2 pi. I have this feeling I'm going to have to adjust. The reason why the x min and max are changed is because we did that zoom squaring, and it changed the x values so that they would be more in line with the y values to make it look like a circle. We'll keep it like this for now. I'll increase things as I need. Let me hit the graph and see what happens. Okay, it looks to me like graph is off of the page, so I'm going to stop this. I'm going to press on. That'll stop the drawing. Let's go to the window. I am going to change this. It's drawing too slowly for me, so I'm going to change this to 0.1, the t-step to 0.1. My x-min, I'm going to go -2. Enter, and my x-max, I'm going to go 2. I don't care about x-scale, really. The y-min, I'm going to go -2 to 2, and let me see if that's enough. I'm going by these two. Since sine and cosine's maximum output is 1, or lowest output is -1, these should go from -2 to 2 in all directions. Let's take a look at the graph now. And you can see with my more aggressive t-steps that it does it much faster. But still, it started still at this place here at the x-axis, and then proceeded to go counterclockwise. So when you draw something like this, hopefully you can do better than me, but if you may be asked to draw a picture of it and give what they call direction arrows. That would be these things I was talking about. Draw in the arrows that indicate the direction that it's traveling, if you will. Now those aren't part of the graph, but they're there to indicate that it's being drawn in a counterclockwise direction. Or they may say in agreement with increasing values of t. Let's try another one. And here you can do, let's try the same thing as before. T will go from 0 to 2 pi. So I get a complete graph. So I'll put these in here. Clear out my x, and I'll put 3 cosine of t. And then for the next one, I'll put 3 sine of t. And I think I can just start deleting the rest of this stuff. Now, I am not going to adjust the window just yet. I still got it from 0 to 2 pi, but let's take a look at the graph. Nothing. If you ever get a graph of nothing, try this. Click on your trace button, and it tells you what the x value is and the y value is, as well as 0. T equals whatever the t value is. And as I move it, these values are simply off the screen. So if I go back to t equals 0, I know that x is 3. Well, that's over here somewhere. So let me change. Well, so these will tell me. I think I'll do x will go from -3 to 3 because cosine goes from -1 to 1. Sine goes from -1 to 1. So y probably goes from -5 to 5. So let me change my x's to go from -3 to 3. And my y's to go from -5 to 5. Let's take a look at this graph now. I made a mistake. Make that into a 5 and try it again. There we go. Now, it's hard to see that this actually is an ellipse because I've made it so that x goes from -3 to 3 and y goes from 5 to 5. So anytime you want to see a more realistic portrait of it, hit zoom 5. It squares it in, and you can see that it's an ellipse now. You can see that it goes from -3 to 3 in the x direction, and it goes from -5 to 5 in the y direction. So here's that picture again, enlarged a little bit so we can see what's going on. And we see it started once again here. This was t equals 0, and proceeded to go in a counterclockwise direction, as indicated by my arrows. And you can see it spans from -3 to 3 and -5 to 5. At some point, assuming you stay in this and even go into Calc 3 or something like that, you'll know what this graph is just by looking at the equations. In fact, let's go back to the original one first of all. And notice that you could think that there was a 1 in front of the cosine and sine here, and that way the width was 1. Well, the width was 2, but the radial width was 1 and the radial height was 1. They were the same. If you go down to the next one, the radial width, or the radius, the semi-major radius, or the minor radius, I don't know what it's called, is 3, which agrees with that number there. And the major radius is 5, which agrees with this. And had I stopped anywhere before, like say I only went from 0 to pi, it'll only draw part of the circle. So let's do a couple of these. Just do them along with me. I need the window. If I want to go from 0 to just pi and graph it now, it'll only do half of the thing. It'll only draw the first half. Because you can see 0 starts in agreement that we've always had was that 0 starts with the positive x-axis. That's where angles of 0 start. And they increase as you go counterclockwise. So by the time I get here, I have pi radians covered. And you can adjust this however you want. If I wanted to change it to, I don't even have to start at 0 if I don't want to. I can start it at negative, say, pi over 2. And I could end it at, say, pi over 2. And you'll see that negative pi over 2 will be here. It'll draw just the right half of the ellipse. And there you have it, starting at negative pi over 2 and ending at pi over 2. One thing I don't know if you can do, and I'm going to try it now, is I don't know if you can start at pi over 2 and end at negative pi over 2. I think you can, but let's see what happens, what the calculator yells at me or not. It did not like my range, so you cannot do that. Although in mathematics you can certainly do it. But this requires that, I'll just have to quit here. This requires that your start be less than your end. Alright, so let's throw this on into the calculator. I'm going from -3 to 3 for my t values. Let's go to the y equals, clear out my first entry, and I'm going to put t to the third minus 1 and let me change my window so at least you get the t starting from -3 and ending at 3. I don't know about the x or y values just yet. Let me just go ahead and graph this and see what happens. All right, I don't see a lot of the graph. I see a little piece of it. So if I want to catch more, I'm going to trace and see where my x values are leading me. When it's at the starting point, x is -28 and y is -14. So I better adjust these things. I'm going to change my x min. I think I'll go -30. And the x max, just to be symmetric, I'll go 30. The y min, I'll do -15. The y max, I'll go to 15 and see what happens. Oh, that looks good. That's a little bit better then. And you can see the way it was graphed. And you can slow it down by how I showed you, but you could see that it came in from the left and snaked up this way. So those arrows indicate what exactly that thing's been doing there. You could also graph this by eliminating the parameter. That means to make the t go away. A lot of people find it easier to graph by not having a t involved. Say you didn't have a parametric grapher, for instance. Let's do this again, but I'm going to show you how to eliminate the parameter. What you want to do is try to make it graphable where x is a function of y or y is a function of x. Since we're used to y being a function of x, I'm going to solve the first equation for t. So the first equation was x equals t cubed minus 1. I'll add 1 to both sides and get x plus 1 equals t cubed. And then I'll just take the cubed root. So t equals the cubed root of x plus 1. And then y was equal to 5t plus 1. So since y equals 5t plus 1, I can substitute this expression in for t, and I'll get y equals the cubed root of x plus 1 plus 1. And then let's go ahead and graph that, and you'll see we get the exact same thing. So, but in order to graph it that way, I've got to change my mode back from parametric to function. Now that that's done, let me go to my y equals. Oh, I already have it in here. But I'm going to put it in just so you can see how it goes. 5. Now you can try to look, I think there is a cubed root thing here, but I hate looking around for it. So instead of using the cubed root, I'm going to go x plus 1, and I'm going to raise it to the 1/3 power, and then bring it down plus 1. Now, we had x min and max set for their corresponding numbers. This time now, x is what we call an independent variable, and y has to use whatever x does to determine what it's going to do. So y is referred to as the dependent variable. So x is going to start somewhere around -28 or -30, I don't remember where, and will end when x gets to 30. So it should trace it in the same manner as it did before. Let's take a look at the graph. And as you can see, here it goes. Zoom up and then over. You get the same graph as you did before. Let me do another example of eliminating the parameter. Suppose I have x equals e to the 2t, and I have y equals e to the t plus 1. And I want t to go from 0 to 25. Now, if we eliminate the parameter and try to write this where I drop the t from everything, a big mistake would be trying to solve the first equation for t. I'll show you why. Well, maybe not. Let's see here. So x equals e to the 2t. So this is still the same thing as before. Let's eliminate the parameter. Well, how do we solve this for t? Well, you take the natural log. And then you can divide by 2. You could even have fun with this and rewrite it as the natural log of the square root of x, because you take this half and bring it as a power to x. Then your y equals e to the t plus 1. Let's plug the natural log of x in for t. It was fortuitous that I did this, because the e and the natural log will cancel each other out, and you'll end up with the square root of x plus 1. So when you graph it, well, you know what this thing looks like. I don't think I have to bother with a graph. X would start at 0, and when x is 0, y would be 1. And then from there, it would go like this. These things up here would give you the same graph, except you have to be a little careful here. You'll notice that e to the t is never equal to 0. When t is 0, you'll have e to the 0 plus 1. That's actually equal to 2, and x is equal to 1. So to be honest, you lose track of where t started and ended when you go to this. Here, if you graph it, unless you knew what I just told you, you would think this starts right at the x-axis, but there's no, e to the t is never 0, so x can't be 0. X can't start at 0. Technically speaking, it starts when x equals 1 and when y is equal to 2. So this part here is not even in there. If we graph this instead, the t will tell us where it starts and ends. So instead of eliminating the parameter, I could put x1t equals e to the 2t, y1t equals e to the t plus 1. Now let's see what the graph does. Change the mode back to parametric. Double check that you're in radian measure. If you're not in radian measure, every answer basically is going to be wrong. Let's go into the window. We're going to go from 0 to 25. And did I put these in yet? No, I did not. I'll put x was e to the 2t. And let's graph it. You can see it looks like it may actually looks like it starts at the y-axis, but I don't think it does. If we trace, you can see that when t equals 0, x is 1 and y is 2. So I could probably get a better visual of this if I change my window from, let's do my x min. I'm just going to do -1, so I have a little cushion on the left. And the x max, I don't know. These get awful big. let's make it 10. I'll do the same with the y min. I'll start at -1 for my lowest y, and then 15 I guess is fine. Let's take a look and see. And you can see there it is. It starts out there at 1, 2. It doesn't actually start at the y-axis. This, of course, you should recognize this is part of a parabola. If it had its way, it would be the whole thing. It would be a sideways parabola. Now, I've sort of indicated that having a facility to tell what's going to be graphed with various equations is very useful. For instance, if you see an equation like this, or a pair of equations like this, and you know that t goes from 0 to 2 pi, this is going to be a circle that's centered at the origin with radius 6. How do I know that? Well, it's because of these numbers and these guys right here. Remember, when I didn't have the 6, I just had cosine t and sine t. When you multiply both of them by 6, you're multiplying both directions by 6. So if without those 6's you had a circle of radius 1, if you multiply everything by 6, it'll grow it to a circle of radius 6. And I'm still at the origin because the things start like it did before. When t is 0, I'm going to start 6 cosine of 0 will be 6 for x, but y will be 0. So when you go and you graph it, here's what will happen. You probably, it's not a bad idea to graph these the old-fashioned way. Make yourself a chart where you have t values and then you have the x, y values. You might find it useful. When t is 0, I have a 6. Then I'm going to jump by pi over 2. So when t is pi over 2, you'll have 6 cosine of pi over 2. So the x part will be 0, but the y value will be 6. And then if you go to pi, this one will be -6 and the second equation will be 0. So it may not look circular when I am done here, but I want you to know that it is a circle of radius 6. What if I wanted to draw a circle? Fine, so we got the radii, but they're always centered at 0, 0. How do I get one that's not centered at 0, 0? Well, you can do similar to what I just did. And let's say I wanted a circle of radius 10. So let's do a circle of radius 10 centered at, let's say, 2, -5. Well, the way you treat this is almost like 2, -5 is your center, okay? And things, if you're going to have a circle of radius 10, if this were a 2 and a -5, then your x starting point would be 12 and your y starting point would be -5. So the way you can shift the circle, if you will, to this point is to do it in this fashion. I can write x minus 2 equal to 10 cosine of t, y minus -5. Now what it does is the center will be -2, 5. That'll be there, except now about that point you'll have a circle of radius 10. Take a look. All I got to do is solve it for x. So I will put y. So I'm not going to put this into the calculator. What I'm going to put is 10 cosine of t plus 2. Similarly, down here, I'm going to put 10 sine of t minus 5. Be careful with your parentheses. Let me check my window. I'm going to start my t min at 0, but my t max will be 2 pi. Got it. I'll leave my t step the way it was. Now if I'm right, and this is a circle of radius 10, then I need to have, if my center is x equal to 2, then I need to stretch from negative 8 to 12. So I'm going to do that. Negative 8 to 12. Similarly, with the y values, if my middle is negative 5, I need to go to 10 in either direction. So I need to go from a low of negative 15 to a high, let's see, negative 5, to a high of 5. And let's take a look at the graph. And there it is, perfectly encapsulated. I'm going to zoom square it so that it looks like the circle it's supposed to be. So let's see if I can locate 2, negative 5. X equals 2. This will be x equals 2. 1, 2, 3, 4, 5. Here's negative 5. See if I can get it right on there. There's my center. 2, comma, negative 5. And the circle you see is of radius 10. Now, as I said before, you can, if you want to draw just parts of the circle, a little bit of practice. Here, this one was done so that t went from 0 to 2 pi. You can play around with this and graph just parts of a circle if you want. If I ask you how was the circle drawn, in what fashion, draw me arrows to show me how the circle was drawn. I simply mean for you to draw these little things here. Little arrows that tell me the direction of travel with increasing t. Of course, it's hard to see those things, so you might want to make them a little more bold than I am. So all this is well and good. We need to do calculus with it. And what we're going to concentrate on, right now at least, are derivatives. And the way we do this is we still, the slope of a curve is dy over dx. Now, however, if you're given in terms of t, you don't have this luxury here where y is defined in terms of x unless you try to eliminate the parameter. That's not always possible to do that. So what we come up with is you might remember this. When we talk about differentials, the definition of dy goes like this. It's dy over dx times dx. That might seem sort of strange, but dx is actually equal to delta x because x is the independent variable. So dx and delta x are the same. Okay, now if x of t and y of t are both functions of t, then t is the independent variable and x comma y are dependent variables. What that means is I can define dy and dx. dy can be written as dy over dt times dt, and dx can be written as dx over dt times dt. Well, what that means for us is then when I try to do dy over dx, the dy I'm going to replace with dy over dt times dt, and the dx I'm going to replace with dx over dt times dt. and the dt's can cancel. So the derivative, dy over dx, simply equals dy over dt divided by dx over dt. So as an example, let's graph x equals 4 minus 3t, y equals negative 2 plus 6t, and let's do t goes from 0 to 10. So let's go ahead and throw these in the calculator and see what happens. And I want to watch carefully how it draws it. So let's go y equals, I think it's easier. Tried editing is not so great, so I think I'm going to clear these out. And in my x1, I'm going to put 4 minus 3t. And y is negative 2 plus 6t. And let me put my window. I'm going to put 0 to 10 for t. I don't know what x and y are going to be just yet, so I'm just going to hang on and just do a graph and see if I see any of it. I see a little bit of it. If I trace, tracing is another way to see how the graph is drawn out. You can see that the graph starts at the bottom and moves diagonal up towards the left as t increases. But I can see I'm going to need more x and y, so I'm going to go to the window, and I think what I'll do is my normal business. I'll do negative 10 to 10 for each of the x and y's. That's usually a good starting place. If that's not enough, I'll increase again. Negative 10 to 10. Let's take a look at that graph again. Oh, there it goes. I don't know if I got all of it up there, so I'm going to give more y to this, and maybe I'll go to y equals, well, I don't know, let me throw in 20, or 10. 6 times 10 is 60, minus 2 is, so I should have had, if I want to catch all of it, y needs to go all the way up to 58. And x needs to go down to negative 26, so let's do negative 26. And the y values have to go up to 58. And let's see if I get the whole thing then. Yeah, there, it spans exactly what I was thinking of. So let me go ahead and take this snapshot of this picture. And as was noted before, the traveling goes up to the left diagonally, like in that fashion. Starts down here. Now we know that this is a line, and I can easily get the slope of the line, but another way that we get the slope of a line is to take the derivative. So find, I don't like that word, especially determine, but find dy over dx. Well, according to what I just wrote, it's dy over dt divided by dx over dt. Well, take the derivatives. Go to what y is, look at the y. What is the derivative of y with respect to t? That's just 6. How about x? Take the derivative with respect to t. The derivative of x with respect to t is negative 3. And that equals negative 2, which is constant. As we know, this would be a line of slope negative 2. And that makes sense because this looks like it has a it has a negative slope. That it's 2 is something I couldn't tell you by looking at it. But your calculator can help you out a little bit as far as checking your work. What you can do is you can press second, trace. That will take you to the calculus menu. Second, trace. And here it gives you the different things that you could calculate. Hit number 2 for dy over dx. and it will let you specify wherever it is you want to go to. So I'll pick any indiscriminate spot here, t equals 3.9. I really don't care. But when I hit enter, it gives me the slope, -2. So this is a way of checking yourself. Now, granted, this is a pretty simple equation, and you could have gotten rid of the parameters here and made y a function of x and had your slope-intercept form and all that kind of stuff. But as I mentioned, there are times when you cannot eliminate the parameter. So let me do one more example and end it there. So in this case, I'll have x equals t to the 5th plus t minus 1, and y will equal the square root of 1 plus t cubed. Now that I think about it, you could actually solve this for t. The second one here for t, if you squared both sides, subtracted 1, and then took the cubed root. So I think I'll make this more difficult than that. I'm going to put a t to the 4th in here so that won't. So this is a real example that I don't think will be very pleasant to try. And I can always put more t terms in between here, but you get the idea. Let's say if t goes between 0 and 3, although that's not important for this example. When I do dy over dx, that will equal dy over dt divided by dx over dt. It almost looks like it follows the reciprocal rule for multiplying or dividing by fractions. And that's the notation was designed to do all that. Let's look at the derivative of y with respect to t. I will get 1 over 2 radical 1 plus t to the 4th. Then don't forget the chain rule says we have to take the derivative of 1 plus t to the 4th. I'll get 4t cubed. And then in the denominator, I'll get 5t to the 4th plus 1. So you can do a little simplifying if you want. Well, I think I'll do a little bit here and here, put 2 there, and maybe flip fractions and things like that. And when all is said and done, I'm going to get 2t cubed. Although you don't have to do any of this stuff. Whatever you need to do to make these simple to yourself, stick with that. So what I could do then, what if I asked you this? Now, compute dy over dx, but evaluated when t equals 1. Well, all you do is plug in t equal 1 into this formula. So 2 times 1 cubed all over 5 times 1 to the 4th plus 1, square root of 1 plus 1 to the 4th, and that equals 2 in the numerator. Down here I get 6 square root of 2. So I can do a lot of simple. The square root of 2 goes into 2, the square root of 2 times. So I'm going to have the square root of 2 over 6. You can do other things. I really don't care about this. Simplifying this, it means nothing to me. I'm just doing it to make the calculation easier. Anyways, so there's my answer. Let me have my calculator check it out on me. Let me put this back. Put these things in here. Let's clear this. T to the 5th plus t minus 1. And then for the y values, I'll do second, the square root 1 plus t to the 4th. And then I'll delete. I told you before it wasn't such a good idea to edit these things, but I guess I survived that one. My t values, I said, went from 0 to 3. The x values, I'll leave like that for now. Let me just take a look at the graph and I'll adjust as needed. So I see it's way over there. So let me trace to find out where my graph is. When t equals 0, we start at -1, 1. And kind of goes from there. It looks like my y values, I don't need to be so big. So let's do my y values. I don't know, let's go -1 to 1 for one thing. The y values, let me take a look at a graph. Eek. Oh, y's actually were bigger. It started at 1, so I did exactly the wrong thing there. I'm going to start my y value then. Start my y min at 0, and maybe I'll go up to 5 with it. Let's take a look again. Okay, now I need more x is what I need. I don't need that low of x, but I need more x that way. So I'll start my x min. I saw it started at -1, so I'll go -5 just to have a little buffer. And then the x max, 3 to the 5th, is that 81, 84, 83, so 85 here. I think that'll take care of it. There we go. It went off the screen, but you get the idea. Now what I wanted to do was check this derivative using the calculator. So I want to do it when t equals 1. And now since my window is set to go by 0.1s, it will land on a whole. If you wanted to make this easy on yourself, you can make your t step equal to 1, and then it will just do 0, 1, 2, and 3. Take a look at the graph. It's broken, but when I go and do the calc, and I choose my value, dy over dx, I'll change it to t equal 1, and I'll hit enter. You see what it gives me? 0.2357. That's what my calculator tells me, 0.2357. Well, I have this. Is that 0.2357? Only one way to find out. I'll quit this, and I'll take the square root of 2 and divide it by 6. Remember, 0.2357. And 0.2357 it is.